So we have seen that searching becomes more efficient if we have a sorted sequence. So for an unsorted array or a list, a linear scan is required and this takes order n time. However, if we have a sorted array, we can use binary search and halve the interval we have to search with each scan and therefore take order log n time. Now sorting also gives us as a byproduct some other useful information. For instance, the median value. The median value in a set is a value such that half the values are bigger and half are smaller. So once we have sorted a sequence, the midpoint automatically gives us the median. We can also do things like building frequency tables or checking for duplicates. Essentially, once we sort a sequence, all identical values come together as a block. So first of all, by checking whether there is a block of size 2, we can check whether there's a duplicate in our list. And for each block, if we count the size of the block, we can build a frequency table. So let's look at some ways to sort sequences. So forget about arrays and lists for the moment, and let's think of sorting as a physical task to be performed. So suppose you are a teaching assistant for a course, and the teacher or the instructor has finished correcting the exam papers and now wants you to arrange them so that the one with the largest marks, the highest marks, is on top, the one with the second highest marks is below, and so on. So your task is to arrange the answer papers after correction in descending order of marks. The topmost one should be the highest mark. So here is one natural strategy to do this. So what we can do is repeatedly look for the biggest or the smallest paper. Now in this case, we are going to build up the stack from the bottom. If the highest mark is on the top, then the lowest mark will be at the bottom. So what we do is we scan the entire stack and find the paper with minimum marks. How do we do this? Well, we just keep looking at each paper in turn. Each time we find a paper with a smaller mark than the one we have in our hand, we change it and replace it by the one we have just found. At the end of the scan, in our hand, we will have the paper with the minimum marks. So initially we assume that the topmost paper has the minimum marks and we keep going down and replacing it with any lower mark we find. So after this scan, we take the paper we have in our hand and put it aside and make a second stack where this is the bottommost thing. Now we have n-1 papers. We repeat the process. We look for the minimum mark amongst these n-1 papers and put this second most lowest mark overall on top of the one we just put. So now we have two papers stacked up in order. As we keep doing this, we will build up a stack from bottom to top, which has the lowest mark at the bottom and the highest mark on the top. So suppose these are our 6 papers. So we have papers with marks 74, 32, 89, 55, 21, and 64. So if we scan this list from left to right, okay, then we will find that 21 is the lowest mark. So our strategy says pick up the one with the lowest mark and move it to a new sequence or a new stack. So we do that. Now again we scan from left to right. This time of course 21 is gone, so we only have 5 numbers to scan. So we will find that 32 is our next, and then proceeding in this way, at the next step we will pick up 55 and then 64 and then 74 and finally 89. So in this way, by doing 6 scans on our list of 6 elements, we have built up a new sequence which has these 6 elements ordered according to their value. So this particular strategy, which is very natural and intuitive, has a name. It's called selection sort, because at each point we select the next element in sorted order and move it to the final sorted list, which is in correct order. So in the algorithm that we executed just now, we needed to build up a second list or a second sequence to store the sorted values. So we kept pulling out things from the first sequence and putting it in the second sequence. However, a little bit of thought will tell us that we don't need to do this. So whenever we pull out an element from the list as being the next smallest, we can move it to the beginning where it is supposed to be and exchange it with what is at the beginning. Right? So we can swap the minimum value with the value in the first position. After this, we look at the second position onwards and find the second minimum value and swap it to the second position and so on. So if we were to execute this modified algorithm on the same input that we had before, so in our first scan, we would start from the left. So the first position is 74, but the minimum is at 21. So now instead of moving 21 to a new list, we will now swap 21 and 74. So 21 comes to the beginning and 74 goes to the position where 21 was. Now we no longer have to worry about anything to do with 21. We only need to look at this slice, if you want to call it that, starting from 32. So we do this and we find the second smallest element. Now the starting element is 32 and the second smallest element also happens to be 32. That is the smallest element in this slice. So we just keep 32 where it is. Now we start the next slice from position 2. So the beginning element is 89, but the smallest element is 55. So having finished this scan, we would say 55 should move to the third position and 89 should replace it. So this way we just keep going on. Now we put 64 where 89 is, and finally 74 is in the correct place and 89 is also in the correct place. And we have a sorted sequence using selection sort, where instead of making a second sequence, we have just systematically moved the smallest element we have found to the start of the segment or section that we are looking at right now. So here is a very simple Python function which implements selection sort. So the main idea about selection sort is that we have this sequence, okay, which has n elements to begin with. So the first time we will scan the entire sequence and we will move the smallest element to this point. Then we will scan the sequence from 1 onwards. Then we will scan the sequence from 2 onwards. And at each point, in whichever segment we will move the smallest element to the beginning. Right? So we have the starting points of each scan. So the starting point initially starts at 0 and then it goes to 1, 2 up to the length of L minus 1. So for the starting values from 0, implicitly this is 0, remember, right? 0 to the length of L minus 1. We first need to find the minimum value. So we assume that the minimum value is at the beginning of the position of the slice. So we set the minimum position to be the starting position. Remember, the starting position is varying from 0 to the length of L minus 1. So each slice, the starting position is the first position in the slice we are currently looking at. Then we scan from this position onwards, and if we find a strictly smaller value, if L of I is smaller than what we currently believe is the minimum value, we replace the minimum position by the current index. So in this way, after going through this entire thing, we would have found that, say, this position is the position of the minimum value. Then we need to exchange these two. So we take the start position and the min position, and we do this simultaneous swap, which we have seen before. We take two values, we exchange them using this pair notation. So let's see how much time this takes. So in each iteration or in each round of this, we are looking at a slice of length k, and we are finding the minimum in that and then exchanging it with the beginning. Now if we have an unsorted sequence of values of length k, we have to look at all of them to find the minimum value because we have no idea where it is. We can't stop at any point and declare that there are no smaller values beyond this. So to find the minimum in an unsorted segment of length k, it requires one scan of k steps. And now we do this starting with the segment of the entire slice, that is a slice of length n, then a slice of length n minus 1 and so on. And so if we write as usual t of n to be the time it takes for an input of size n to be sorted using selection sort, this will be n for the first slice, n plus 1 for the second slice position 1 onwards, n minus 2 for the position 2 onwards and so on. And if we add this all up, we have this familiar sum 1 plus 2 plus 3 up to n, which you will hopefully remember or you can look up, is given by this expression n into n plus 1 by 2. Now n into n plus 1 by 2, if we expand it, becomes n squared by 2 plus n by 2. Now this big O notation, which tells us that it is proportional to n squared, when we have expressions like this which have different terms like n, n squared, n cubed, it turns out that you only need to record the highest term. So since n squared is the highest term, n squared grows faster than n, we can simplify this to O n squared. If you want to see why this is so, we should look up any standard algorithms book. It will explain to you how we calculate big O, but for our purposes, it's enough to remember that big O just takes the highest term in the expression that we're looking at. We said that a sorting algorithm like selection sort, which takes order n squared, will not work for very large values, say for lengths larger than about 5,000. So let's look at how this thing works. So first so this is the same code that we had on the slide. So selection sort scans slices from 0 up to the length of L minus 1. So let's start the Python interpreter. And now we load selection sort from this file. Now notice the way selection sort works. It doesn't actually return a value. Right? What selection sort does is it takes the value that the list that is passed to it and it sorts it in place. So in order to see anything from this, we have to first give it a name. So let us take a list such as 372, for example, and say selection sort of L. And now if we look at L, it's correctly sorted in ascending order as 237. Now in general, we can take a longer list. So for instance, we can use this range function and say, give me the list which is created by taking the range, say, from 500 to 0 with step of -1. So this is a descending list of length 500. Okay, so if I look at L, it's 500 down to 1. And now if I say insertion selection sort of L, then it gets sorted as 1 to 500. Now our claim is that this will stop working effectively around 5,000. So let's see, if I make this as 1,000 instead of 500 and run selection sort, then you can see there is an appreciable gap. Right? Now if I do it for say 2,000, then there's a slightly longer gap. If I do it for 5,000, then you can see it takes a little bit of time. Right? It takes more than 1 second for sure. So this is just to validate our claim that in Python, if you expect to do something in 1 second, then you'd better make sure that the number of steps is below about 10 to the 7. And since 5,000 squared takes you well beyond 10 to the 7, you can expect it to take a very long time.